Hi, my name is James Nielsen. This is for FTT122, and today's date is April 28th, 2024. The first thing we're going to discuss today is trajectory and sights. Trajectory is the flight path of the projectile. So say here this is our gun, and this is our projectile. When it's fired, it'll exit the muzzle and continue in its trajectory. Sights give you a line of sight that is negative to the bore's axis. And when your sights are aligned with your target, the barrel is actually pointed at a slight positive angle. So to demonstrate here, we have these two shish kebab sticks here. And let's say our barrel was right here at a slight positive angle, and our sights are here at a slight negative angle. They will intersect at what we call the point of zero. Should be right here. Pistols and shotguns have short effective ranges and typically only have one point of zero. Rifles have a much longer range and typically will have 2 points of zero, a near zero and a far zero. This is due to a steeper angle of the barrel. Our barrel was pointed right here, and this is our line of sight. We would actually have our near zero here, and then as the bullet comes back down, we'd have our far zero. Up next, we have gyroscopic drift, more commonly referred to as spin drift. In Harry Palmer's article, What is Spin Drift? Definition on tier1usa.com, he states that spin drift is the horizontal deviation of a bullet's trajectory due to the gyroscopic forces generated by the bullet's spin as it travels through the air. I'll try and demonstrate it here with our pink golf ball. You can kind of see how when you have a spin on it, it'll end up pulling in whatever direction it is spinning in. So this happens because the force of gravity is pulling down on the spinning projectile, and it creates a slight yaw to the right. All right, up next we have drag. Drag is a force that opposes an object's motion through the air. The more aerodynamic something is, the faster it can go and can maintain those speeds for longer. The faster an object goes through the air, the higher the forces of drag will be. To demonstrate, I have a aerosol can cap. Now, as this thing flies through the air, drag is going to exert force on all of this surface, which is going to slow this down a lot faster than, let's say, our unicorn sidewalk chalk. This is a lot more aerodynamic. It's going to be able to cut through the air and have a lot less drag than our cap. All right, next up we have the Magnus effect. The Magnus effect is a phenomenon that occurs due to crosswinds. The combination of the projectile's spin and a crosswind will create a vertical displacement. So if our projectile is spinning here to the right, and we have a right-handed wind, which would be blowing from the left to the right, it'll create a yaw to the left pointed slightly up, resulting in slightly less bullet drop. Now, if we have our projectile again spinning to the right, and we have a left-hand wind, which would be blowing from the right to the left, it will yaw to the right with a downward pitch, which results in more bullet drop. Up next, we have the Coriolis and Evotos effect. The Coriolis effect impacts the projectile on a horizontal plane when shooting from north to south or south to north. The Coriolis effect, when shooting in the northern hemisphere, will always deflect to the right. And that's whether you're shooting from the pole to the equator or from the equator to the poles. It'll always deflect to the right. And that's due to you're shooting at the equator and shooting north, you're spinning faster than the target. And if you're at the pole and you're shooting toward the equator, the target is spinning faster than you are. So you'll always miss to the right. In the southern hemisphere, it's the opposite. You'll always miss to the left. And that's due to the Earth's rotation being faster at the equator than it is at the poles. The Evotus effect impacts a projectile on a vertical plane when shooting from east to west. When a projectile is fired from the west, the target will move towards the projectile and rise in relation to its trajectory, resulting in a low impact. Now the Earth is spinning in this direction, and from your shooting from the west, the Earth's rotation is bringing that target up to the projectile. And then when fired from the east, target is actually moving away from the projectile, resulting in a high impact. And the EVOS effect is always strongest at the equator. All right, up next we have vertical angles. Vertical angles basically come in effect when shooting uphill or downhill. And the steeper the angle, the more prevalent the effect will be. To demonstrate this, I have my two shish kebab sticks and a tall cup. This could be a building. And this would be our line of sight. And this would be our actual distance that gravity is forcing upon that projectile. So when you stand these two up on end, you will see that our line of sight is actually further than what the gravity is acting upon. So this always will result in a high impact. And then lastly, we have transonic ballistic performance. The transonic region ranges from about 788 feet per second to 1340 feet per second. And as we all know, the speed of sound is 1125 feet per second. So right there in the middle of that transonic range. Now earlier I mentioned that the faster an object travels through the air, the more drag force is applied to it. So as the projectile slows down to subsonic velocities, the amount of drag decreases. This creates an imbalance in the projectile and forces it to wobble due to the center of pressure moving forward away from the center of gravity. So it'll start to wobble. If a projectile is properly stabilized, it will wobble for a minute and then it will recover and maintain its trajectory. And if the projectile is not stabilized properly, it can continue to wobble and drift off of its trajectory. That's all I have for you today. Thank you.